Have you ever stopped to wonder, how does AI actually understand what you're saying? I mean, really think about it. When you type some wild, complex prompt into a modern chatbot, how does a machine, which is literally just built on ones and zeros, read our sentences, interpret all of our weird human nuances, and then respond with such startling accuracy? Well, it's a completely fascinating journey of a single word through modern AI. And today, we're going to pull back the curtain on exactly how the whole thing works. So welcome to this explainer. Today, we are absolutely demystifying the transformer. And no, not the robots in disguise. We're talking about the underlying architecture that powers this entire modern AI revolution. We're going to break down these incredibly dense algorithmic mechanics step by step so you can truly grasp how AI understands language. Let's dive in. Okay, here's our roadmap for today. We'll start with Section 1, the AI architecture shift. Then Section 2, turning words into numbers. Section 3, the magic of attention. And finally, Section 4, generating the future. Let's kick things off with Section 1, the AI architecture shift, moving past the slow conveyor belt. Now, to really appreciate the absolute genius of the transformer, we have to talk about the massive bottleneck the AI industry faced before 2017. Back then, we relied heavily on recurrent neural networks, or RNNs, and you can think of RNNs like a really slow conveyor belt. They processed words sequentially, just one after the other, from left to right. This was incredibly slow because it couldn't compute in parallel, and honestly, it really struggled to remember long sequences of text. By the time it got to the end of a paragraph, it kind of forgot what the beginning was about. Transformers changed the game. They threw out the conveyor belt entirely. They process everything in parallel, looking at the full context all at once. It was a total game changer. And what's really interesting is when you look at the timeline. For literally decades, dating back to the 1990s, those sequential RNNs dominated natural language processing. In fact, language AI was actually lagging way behind computer vision at the time. But then, in 2017, this landmark paper drops. It's titled, "Attention is All You Need." And it revolutionized the field almost overnight, proving you didn't need that slow recurrence at all. The idea spread like wildfire, and by 2018, this new architecture gave birth to models like GPT and BERT, essentially launching AI into the mainstream as we know it today. All right, moving right along to Section 2, turning words into numbers, stripping words down to data. So the fundamental problem we have is that machines simply don't read English. They need numbers. Historically, we used a method called one-hot encoding. If you look at how we categorize VW, Acura, and Honda here, you can see how it assigns a 1 to signify presence and a 0 for absence. And we do this to turn variables into strict binary codes so the model doesn't assume any false hierarchies. Like, we don't want the math getting skewed and thinking the mathematical average of a VW and a Honda is an Acura, right? But here's the catch. Imagine doing this for a vocabulary of, say, 100,000 words. You would end up with these massive, incredibly inefficient lists of data that are almost entirely filled with zeros. To solve that massive inefficiency, we create something called embeddings. Instead of a giant list of zeros with a single one, an embedding maps a word onto a multi-dimensional spatial map. The real magic here is that semantic similarity equals spatial proximity. What that means is words with similar meanings literally cluster together, kind of like neighborhoods in a city. This is how the AI inherently knows that a dog and a cat are closer in meaning than a dog and a toaster. It drastically cuts down the computational burden while beautifully preserving all those rich, nuanced relationships between our words. But actually, there is a catch. Because transformers process everything in parallel, remember, they read the whole sentence all at once instead of on that slow conveyor belt, they completely lose all sense of word order. So how do they know the sequence? Well, engineers inject a sort of circular wiggle using sinusoidal functions directly into the embedded representation of the words, positional encoding. And why does this matter? Because without this circular wiggle, the AI literally wouldn't know the difference between the dog bit the man and the man bit the dog. The exact same words, but completely different meanings. This wiggle injects spatial order directly into the math. Which brings us to the climax of our explainer. Section 3, the magic of attention, the library of meaning. This right here is the beating heart of the transformer. Now, the matrix math is pretty dense, so to simplify it, imagine you are standing in a massive library. Your specific word acts as a query. It's basically asking a question of the surrounding text. Now, the keys are like the book titles on the spines. They signal what information the other words hold. Your query compares itself to all the keys to find relevance. And once it finds a match, it extracts the value, the actual contextual payload inside the book, to update its very own meaning. This library dynamic is what we call self-attention. It's a mechanism where every single word computes its relationship to all other words in the sentence simultaneously. Take the word bank, for example. Is it the muddy bank of a river or a bank full of money? Well, by using self-attention to query the keys of surrounding words like fishing and water, or maybe accused and robbing, the word bank pulls the right values to create a highly accurate, heavily contextualized embedding of itself. It's brilliant. Now, under the hood, doing this for every word all at once requires a massive scale of computation. All of these queries, keys, and values are processed as dense matrix multiplications. And there's a great quote from our source material that says, "Matrix multiplication is like a bullet train. If your data can be expressed in its format, it will reach its destination extremely quickly." Because absolutely everything here is matrix math, modern GPUs can process this self-attention across thousands of words simultaneously at lightning speeds. All right, final stretch. Section 4, generating the future, collapsing math back into language. So now that our word has found its deep contextual meaning, the AI has to actually do its job and predict the next token to generate future text. But to do this fairly during training, it uses something called causal masking. This essentially acts like a blinder. It mathematically hides future words from the model by assigning them a score of negative infinity. And since negative infinity turns to an absolute zero in probability, the model is strictly forced to legitimately learn how to predict the next word using only the past context, rather than just cheating and peeking ahead at the answer. Okay, so after the model safely analyzes the past context through all its transformer blocks, it spits out a final dense output vector. But remember, at this point, this is still just a cluster of numbers floating in a lower dimensional space. We need human words. So to get a word back, this vector is multiplied by a de-embedding matrix. This is absolutely crucial. It essentially maps our rich, multi-dimensional math back out into the high-dimensional vocabulary space, which is just a fancy way of saying our massive dictionary of understandable human words. Let's look at this final translation step. That de-embedding matrix projects the output into raw scores, which are called logits, for every single word in its vocabulary. We then apply a math function called softmax, which normalizes all these messy raw scores into a perfect, neat probability distribution that adds up to exactly 100%. Finally, an operation like argmax steps in and simply selects the word with the highest probability. And boom, that single chosen word is the model's prediction. And this brings us to the final piece of the entire puzzle, autoregressive generation. You see, the AI doesn't just spit out a whole paragraph at once. It takes that single shiny new word it just predicted, appends it to the end of the original input sequence, and feeds that whole newly updated sequence right back into the decoder. It adds what it just created to the pile and starts the entire journey over again, predicting the next word and the next, looping over and over until the thought is completely finished. So there you have it. We've seen how transformers moved past the slow conveyor belts of the 90s, turned our words into spatial numbers, found deep contextual meaning through self-attention, and autoregressively predicted the future. But I want to leave you with this final provocative thought. If transformers can master the incredible nuance, humor, and syntax of human language just by playing a highly optimized guessing game with numbers, what happens when these networks start creating highly efficient mathematical languages of their very own to communicate with each other? It's wild to think about. Thank you so much for joining me on this explainer. Keep learning, and I'll see you next time.